All right, I'm going to, Mike, do you want to quickly say hello before I kick across, just to introduce yourself?
Yeah, sure. Thanks, Kelvin. It's just great to be here and to engage with Derek again. And I always learn something from Derek Weiner, so I think it's going to be a great webinar, and we'll try to monitor the chat. Thank you.
Thank you. Derek, I'll hand over to you.
Thank you, Kelvin, and thank you also to the Art of Work Academy for the initiative of putting this webinar on, and thank you to all of you who are here. What I want to do today is talk about the history of this model, first of all, both in science and in its current form. I want to talk about how it developed, just briefly, and then describe and explain the model, of course, and finish by talking about what this model offers us in the context of in what the science of this model offers us, I should say. Now, those of you who are listening here, some of you will have heard of this before, this model, and others of you may not, and it's quite possible that you may find the whole thing has been awkward in your mind. You can't quite put it together with the rest of your safety understanding, and I believe that what I'm going to be talking about today will help you understand that tension, if it exists there. This first slide, let me launch into the science history of this. Back in 1686, Newton came up with his laws, and you will all have heard about Newton's laws of motion. The potential for an understanding of what energy was in the context of those laws was not really fully realized in human mind, in the mind of scientists, until the 19th century. Believe it or not, we're talking the mid-1800s. And at that time, it would have been possible for humankind to actually have seen that what we're talking about there is the foundation science required to understand the problem of safety. But it was overlaid significantly by preconceptions of what safety was all about. Particularly safety or lack of safety resulted in injury, and injury was a result of inappropriate behavior. Inappropriate in the context of some moral code. So our brains, our socialization got in the way of understanding the real meaning of this. The first point in the literature that I'm told about is this man, which you will see on the top left-hand side of the screen there, de Blois, if I'm pronouncing it properly, in 1926, who I am reliably told mentioned the need for energy to be involved in injury and damage. I haven't personally seen that paper. There was, however, in the 60s and the 70s in the USA, a group of people who were put together to research the increasing problem of carnage on the roads. And this involved a perceptual psychologist, J.J. Gibson. And in 1961, he's the first one of that group to actually publish in a rather obscure journal the fact that people operated in an environment which included a number of harmful energies. One of the group was Bill Haddon, the other bold name that you can see there. Bill Haddon was a physician, and he worked along with Helen Sukman, also a physician, and David Klein, a social scientist. And Haddon, 10 years or a little bit more than 10 years after Gibson, published a seminal paper called Energy Damage and the 10 Countermeasure Strategies. And this paper pointed out primarily, the first thing that it pointed out of interest is that science progresses when we understand the process which has given rise to the phenomenon of interest. And his 10 countermeasure strategies were all strategies relating to energy. And I'll explain that. The conservation of energy, or the idea that energy is conserved, the law of conservation of energy, as I said, came in the previous century to the 1900s, in the 19th century, and yet nothing much was done about it. Then I was given the task of putting together a tertiary education course, and in 1978-79, in preparation for this, I looked at what Haddon was doing and applied my, had written about and applied my engineer's view of what I think was a useful way of actually understanding this. And so I'd like to carry forwards in actually sort of looking at how that unwrapped into what is now called the energy damage model. Thanks, Calvin. Next slide. Yeah. One of the things that we need to understand here before I embark upon describing it is the difference between normative sciences and physical sciences. And normative sciences are ones which we invent for ourselves. Physical sciences are ones where we're trying to understand how a physical phenomenon can be explained. And the normative sciences include things like political science, economics, social science, psychology, and tellingly, safety science. Now, safety as a concept is clearly a subjective state of being. It's not something which you can point your finger at or press or throw away or anything like that. And what is safe to one person is not safe to another person. It's entirely subjective. If we compare that, thanks, Calvin, with the characteristics of the physical sciences, they are the sciences that we normally, I think about in this respect: physics, chemistry, geology, botany, zoology, etc. And to that, we can add the science of risk if we frame the science properly. Now, all of these sciences have taken a bit of effort psychologically and socially for mankind to accept. Physics arose out of metaphysics. Newton himself actually was an astrologer before he became an astronomer. And chemistry arose out of alchemy, and so on. Those two old physical sciences. The sciences of geology, botany, and zoology have all proved the point that was made in the paper by Haddon, that we need to understand the process giving rise to the phenomenon of interest. So the science of risk must say, well, what is the phenomenon of interest? The obvious answer is unwanted damage, and we can use that term to include injury, ill health, and so on. And so the science of risk can be based on an understanding of the phenomenon that gives rise to the process that gives rise to the phenomenon of damage. Thanks, Kelvin. Now, there's a big conceptual difference here between these physical sciences approach that I've just mentioned there and the safety science approach. And the safety science approach, I think you will see, is fundamentally indistinct and has no definite phenomenon that it's talking about. And I think that in this, it is sufficient explanation for the fact that in the field of safety, over the years, we have gone from one fad to another fad to another fad. Because there is nothing pinpointing it and bringing it down to earth, so to speak. And it may be these conceptual differences which perhaps are the source of any uncertainty or tension that you might find in your mind when looking at safety and all the energy that goes into it. You've only got to look at what gets published in Safety Science as a journal to understand the massive amount of energy that's put into safety science, so to speak, as a normative science, compared with that which it gets put into it from a physical sciences point of view. From a physical sciences point of view, the term safety science is an oxymoron. Now, I'm not being critical of safety science here. I'm just wishing to point out the fundamental differences and the underutilization in the past of the physical sciences approach to this subject. Thank you, Kelvin. So, in looking at this physical science approach, I'm an engineer, and I was asked to put together a course, a tertiary course in the field of what became occupational hazard management. And I came up with the fact that this process has three characteristics, which are shown on the slide here. Number one is that if damage occurs, necessarily there is an energy involved. It's not a fad, it's not an option, it's a physical necessity. The second one is that this process actually takes time to unfold. And if we look at the process of energy damage in a time-based manner, what comes first and then what happens after that, we gain a lot of understanding of the structure of the process. And the third one is that this process is uncertain. And it's that which gives rise to our perception of risk. So of these three essential features of the process that gives rise to damage, I'm going to talk today about number one, the energy damage model. Thanks, Kelvin. First of all, we need a source of energy, quite clearly. And one of the features of physical sciences is objective definitions. It becomes immediately apparent that we could readily actually define the term hazard, which everybody uses willy-nilly in the social sciences, as a source of potentially damaging energies. Now, in referring to Haddon and his work in his seminal paper, The 10 Countermeasure Strategies, Haddon strategies numbers 1 and 2 fit in here. And as you can see, they are, don't put the energy together in the first place. And the second one is, if you do have to do that, well, reduce the amount of energy marshaled, as Haddon put it. I won't go into a massive amount of detail here to explain that. I think it's pretty self-explanatory. Thanks, Kelvin. Now, the point about a hazard is not that it exists, because we live with them all the time. We drive a car and we're in a source of potentially damaging energy. We use electricity in our houses. There's a source of potentially damaging energy. These damaging energies are around us all the time. And the fact of interest is that they are the potential for damage is controlled in some way. Whether it's a good way or a not way, the potential for damage is always controlled. And so what we're interested in is understanding the hazard control mechanism. Now, Haddon's countermeasure strategies here are prevent the release of energy and modify the rate of spatial distribution of energy from its source. Thanks, Kelvin. If that energy is released in some way, that is the control mechanism fails. And what that means is the potentially damaging properties of that hazard are actually released and open and possible to injure people, to create damage. That clearly, a space transfer mechanism is required to take that energy towards the recipient, as shown in a rather nice way by this slide here. Thanks, Kelvin. Now, the recipient is anything we're interested in and we value. Take ourselves as a classic example, or people, whether they're public or employees or whoever they are. Typically, it's people, but we're also interested in the environment. I think we're also interested in production processes and equipment. So mostly, if we have a crash in our car, it's a panel damage accident, which is going to happen. So we are interested in all of those things. So damage applies to all of those things in all of those types of recipient. Thanks, Kelvin. Now, recipients are are actually naturally protected. You'd be aware that our skin protects us from various things. If we get bumped and so on, we can, sorry, I just have a small glitch on my computer here. Sorry, I'm back again. I'm not quite sure what happened there. So we have protection of some sort, and we can add to that protection by putting ourselves into personal protective equipment. But there is always a protection of us in relationship to incident energies, and we can think of that as the strength of that boundary as having a damage threshold. The intensity of energy that is required to just produce a level of damage is the damage threshold surrounding and protecting a recipient. Thanks, Kelvin. Now, recipients are exposed if they are, if a recipient is exposed to incident energy, then damage is possible. If the recipient is not exposed, damage is not possible. This factor of exposure is well taken into account in industrial hygiene, for example. How much noise should you be exposed to, and what level of concentration of toxic substances in the atmosphere is a reasonable exposure, etc. So the concept of exposure becomes important here also in our understanding of accidents in your car, for example. So the model clearly outlines this well-known parameter of exposure, which is not something which happens in the social sciences. Thanks, Kelvin. So the model requires a source of energy, a means of controlling the potentially damaging properties of that source of energy, a space transfer mechanism, and a recipient. And Haddon's countermeasures, numbers 5 and 6, are to separate in space or time and install a barrier between them. Now, at great personal risk, I actually am here today to demonstrate to you the very simplest form of the application of this model. You may be able to see I've got some patches on my face, which are a bit bloody there and there. These are skin cancer biopsies, and I've been exposed to ultraviolet radiation from the sun, which is the source of all of our energies, or most of them, from the sun all my life. And there is no control over the release of these potentially damaging properties of the energy source, because we don't have a barrier around the sun. What we do have in the space transfer mechanism is a massive distance, and that massive distance actually produces an intensity of energy at my body, which doesn't fry me instantly. It just produces some microscopic, at a microscopic level, some changes to molecular structure, which is what we call cancers. So you can see the validity of it is just very obvious. There's nothing complicated about this model. Thanks, Calvin. So thinking about the space transfer mechanism there, the energy needs to be able to move through space, radiate, if you like. And this slide applies simple principles from the physical sciences to understand how this radiation through space might happen. It can happen either by mass transfer or by a property transfer. Mass transfer, for example, a simple way of looking at this is someone pulls a trigger on a gun, and what radiates out from the gun is a bullet which has a large amount of kinetic energy. And so the mechanism of that is a mass transfer of kinetic energy. we might have high pressure steam emanating from a hole or an open valve or something like that in pipework, or a high pressure toxic gas doing the same. And the physical movement through space is a result of the pressure driving it. So there are these various mass transfer mechanisms which you can read at your leisure there. We've then got also property transfers. For example, heat is thermal energy is a property of air or property of water, and so on. And temperature can be propagated through space. Standing too close, for example, or rather close to a radiant bar heater makes it very clear to you that the heat energy is actually being propagated through space. And so we've got various mechanisms which enable a property transfer to occur, and those are detailed on the slide, all conforming with the laws of the physical sciences. There's nothing that doesn't conform with these laws here. Thanks, Kelvin. So if we have another situation which we need to be concerned with here, which is the possibility that an energy source might actually be mobile. And this slide shows that if we do have a mobile energy source, that all it needs is a space transfer mechanism, its mobility, to actually move through space and direct itself towards the recipient, in which case you might say that there is a space-time coincidence between the energy source and the recipient. Think a falling brick on a construction site. The brick falls. It's a source of potentially damaging energy before it falls. It's got gravitational energy, potential energy. And as it falls, it develops speed. And if a person happens to be walking underneath it, there is a space-time coincidence. And that energy comes to a rest on the head of the person walking underneath. It's a very simple set of concepts here, but that's one possibility for the space-time, for the space transfer mechanism, I should say. Thanks, Kelvin. An alternative, of course, is actually that the recipient actually moves towards the energy. A classic example of this is a person feeding a machine with their hands, putting stuff into a machine, pulling it out of a machine. Their hand can be going into what is a damaging energy space, as long as that damaging energy space is energized. And so in that situation, you can find somebody putting their hands into the machine at the wrong time, for example, and getting their hand crushed. The case I came across was a man who slipped into a channel containing very high temperature water. It was all but boiling. And his body moved physically because of the fall into the channel. And he was exposed to uncontrolled thermal energy. There was no control of the around that energy to prevent him actually contacting the energy. And of course, he died. So that's another version of a space transfer mechanism where we have a mobile recipient. Thanks, Kelvin. We then have the other one, which is where the recipient and the energy source actually coexist. So all of us are in this situation. We all have weight, gravity, potential energy, and if we could also have kinetic energy if we're running. So these typical mechanical energies are ones that we have, and they're well able to actually injure us. I've known situations where somebody has had an amputated finger from a wedding ring being caught on the side of a truck body while they were falling off the truck, and they left their finger behind because the ring amputated it. I've also known of a situation of somebody's finger being amputated by an energy source, which is their powerful muscles in their thighs. So we can conceive of various situations in which energy within the body of the injured person is actually the energy source, energy form that actually gives rise to the injury. So we need to be flexible in our understanding of the way in which the model works, with an energy on one side and the recipient on the other side. So these simple structures give us a very clear idea of this. Thanks, Calvin. And so if we look at what we can do about this, because this is a practical applied science, it's not just a theoretical science, we're interested in control measures. So how do control measures identify themselves here? So the number one basic principle is that we control the existence or amount of the energy as shown on this slide here. And if we then move on to the next control, thanks Calvin, we can see that it is actually over the hazard control mechanism, that mechanism which maintains control over the potentially damaging properties of the energy source. We could say as engineers, this is not an absolute. It's not that the control mechanism is either there or it's not there. We're interested in the reliability of that hazard control mechanism. It's a probabilistic thing for engineers in the real world. Thanks, Calvin. Then, of course, there is the space transfer mechanism. We need to remove or reduce the need for the space transfer mechanism. So if we put a noisy machine inside a vacuum, for example, there is no possibility of the noise radiating out from beyond the vacuum, because noise by definition is a pressure wave in air. Or we could put a barrier in there which is absorbing the noise. So these simple ideas. Thanks, Calvin. We can also strengthen the damage threshold, raise the damage threshold of the recipient. All these are fairly clearly indicated in this model, and the next control measure becomes fairly apparent, thanks, Calvin, which is that we get rid of the recipient. We take the recipient out of the way of the direction of an uncontrolled release of energy. We separate the hazard and the recipient. So Haddon's 10 countermeasure strategies actually break down into 5 groups in this particular way. Thanks, Calvin. So it's very easy for us to maintain in our mind this simple model, and without any effort required in our minds to actually know where the possible countermeasure strategies are. That Haddon broke down into a much larger number. That's not to say that Haddon was wrong. He's not wrong at all. I'm not meaning to imply that, but this is a little bit more, perhaps a little bit more memorable and easy to recall than Haddon's 10. Haddon's 10 actually include rehabilitation and damage control efforts and so on. So that's how he gets a little bit more out of it than that. Thank you, Calvin. Now, another feature of this is that energy damage doesn't happen as a single sudden blast of energy always. Sometimes it's different. And so we've got what I categorize here as 3 types of energy damage duration categories. The one on the bottom I've labeled discrete, a large amount of energy in one fell swoop. That's your car crashing into a lamppost or a tree or anything similar to that. That's your typical accident, which people talk about in the normative science of safety science. On the top is labeled another arrow, which is called continuous. So if we are, for example, working in a workplace in which in close proximity to, say, a fan produces a regular output of energy, so that there is no control over the release of the damaging properties of the energy source. It's just required to be constantly working. And so we are exposed to that incident energy constantly. You can, of course, I'm sure, understand, you can relate to that with chemicals, chemical dust exposures, vapor exposures, and so on. Also with heat, with UV radiation, and so on and so forth. And just for completeness, we also have in there the middle arrow there, a whole lot of little arrows, which I've labeled multiple discrete. A hammer blow, bang, 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 for example. Sometimes there are some circumstances in which the noise is a classic one of these, where the peak energy release in the bang process occurs so rapidly that the ear is particularly sensitive to it, because the ear doesn't have time to respond to shut down the process of the sound energy through the ear into the inner ear. So multiple discretes are sometimes particularly important. Thanks, Kelvin. So that's basically the essence of the model. We need to understand something of the way in which energies can be categorized to make use of that model. There are various ways, if you look online, at which you can see that people have actually attempted to categorize energy. For example, if you look at a microscopic level at temperature, what we perceive as temperature, it actually consists of an awful lot of kinetic energy in molecules which are bouncing around because they're so energized. They're full of energy that they don't know what to do with. And that actually becomes kinetic energy. And guess what? Pressure in a pressure vessel is also formed in the same way. It's a whole lot of molecules inside bouncing around, wishing they could get out of the walls of the pressure vessel. So at a microscopic level, it's possible to categorize energy forms in a very small number, which are often kinetic energy or one or the other. So if you were to do, after this, have a look at categorizations of energy forms on the internet, you will find some microscopic ones. Now, microscopic ones are actually of some value in some areas of energy categorization, but not all of them. So for an engineer, it's a little bit more interesting to talk about the pressure energy contained within a pressure vessel than it is to talk about the molecular kinetic energy. And in fact, the term, the measure that we use for pressure is actually the energy required to raise a unit volume of whatever is inside the pressure vessel to that pressure. It's an energy-based statement, and indeed voltage is an energy-based statement as well. It's the amount of energy required to move a unit of charge up to that higher potential. So our categorization from a practical perspective for us on Earth trying to do something about the damaging properties of these energies is to look more at a macroscopic level of energy rather than the microscopic. And this categorization, which I'll show you here, is based upon that. So we've got the gravitational potential energy, the pressure energy, kinetic energy, and so on. Probably not very difficult for any of us to understand, but I just wanted to make the point about how do you categorize the energy. Next one, thanks, Calvin. Acoustic and vibration, much the same things. Noise is just a vibration, a pressure vibration in air, whereas vibration is a what we call vibration is just a mechanical vibration in solids. We've got electricity, ionizing radiation, and we've got heat. I've already talked about those. Thanks, Calvin. Chemicals, probably the correct term here is chemical bonding energy. A large amount of energy can be stored in chemical bonds, and these can give rise to burning with a heat release. They can give rise to a sudden flash burn with a massive heat release, and they can give rise to explosions as well. Now, microbiological here doesn't seem to really fit very easily, perhaps, with me, but when I was giving this talk many years ago to a group of a group of medical doctors who were getting a postgraduate qualification in industrial medicine, I raised that I didn't find this fitting the model particularly well. And the response to a person there were about 12 of them, was no, they didn't have any difficulty at all in seeing the way bacteria, viruses, and fungi operate within the body. They were quite happy with that being categorized as, say, microbiological energy. Next one, we've got muscles. And we've got one in here, psychosocial, which is all the rage at the moment in health and safety, as in a safety science approach to this. It should actually be called a psychosocial stressor, not a psychosocial hazard. And the subject of stressors, physical, psychological, and social, and their stress reactions in the body, which can be physical, psychological, or social as well, is a science in its own right, and a science which I think is much misunderstood or perhaps not recognized as existing by typical safety people working in the safety field. Thanks, Calvin. Now, these can all be applied to recipients, which I've mentioned before, are people, environment, equipment, and so on. Thanks, Calvin. Now, using this, we can actually learn a lot from the typical methods of science, and I'll just go through the headings here. And one is that we can easily produce standardized models. Fires always occur in the same way, or in a collection of different ways, which we can easily predict before we even look at a fire. Ditto, control types can have certain categories of control types, which we can learn from. And then also risk factors. We realize that actually what makes one fire different from another fire is actually not the underlying chemistry or anything like that. It's the risk factors, which are all to do with the circumstances and conditions surrounding the situation. Medical science is very familiar with risk factors, and I'm sure you are. If I was to say to you, what are the risk factors leading to heart attack? I wouldn't mind betting you could easily rattle them off. And the reason why you can do that is because science of this nature has been applied to that subject. Thanks, Calvin. So the energy damage model can be summarized in all of its complexity and simplicity in this single slide here. So while I've spent a bit of time talking about the nuances of all of this, I think you can see the fact that one slide will actually encapsulate all of this makes you realize that all of this can be held in the brain and made use of as needed. There's a lot more that could be said about the energy damage model, but that's all I think that I need to talk about today as an introduction to it.
Thanks.
So yes, so just a brief summary. A history of of where it comes from in science generally and in human beings' ability to adopt that, a description of the model, and an understanding of the scientific implications of it. Thanks. Sorry, Kelvin, I interrupted you.
No, I thought just thanks. That's been a really interesting, and I think the way that you've broken down, starting from the history of this, moving through the scientific context, and then explaining the concept and how it works with practical examples, and also then introducing the energy concepts. I think it's really useful. I'm going to hand across to Mike for some questions in that space, and then we're going to open up to everyone in the call to put some questions to you as well. So Mike, I think you had a couple of questions to pose to Derek.
Sure, and I think it'd be great to get our audience also involved as well too. Derek, if from a design perspective, could you just talk generally or specifically about the utility of the model from a design or a design thinking perspective?
Thanks, Michael. Yeah, the thing that I found satisfying about this model as it unfolded was its underlying simplicity and yet also its comprehensive coverage, if you like. And to the engineer in me, that's very helpful. But what becomes apparent to me in the model was that doing something about the level of energy that you've got in the first place is a design problem. So if you're designing, for example, this is just an illustration that comes to my mind. I don't suppose many of us are going to go out and design a petrochemical plant tomorrow, are we? But just to illustrate the point, if you've got a petrochemical plant which needs to store 1 million liters of flammable material, do you put all 1 million liters in one tank, or do you split it up into 100 tanks so that each tank is a much smaller inventory, which is Haddon's idea here. Don't put so much energy together in one place. From another design point of view, if you're doing something like making paint, for example, do you use a toxic solvent as the base of the paint, or can you in fact create the base of the paint out of something which is not toxic, like water, for instance? That's a design problem. And then when it comes to the hazard control mechanism, that's fundamentally a design problem. You either manage that well or you don't. I remember very clearly walking through a steel plant one day with a very senior safety engineer, and he was asking me questions about this energy damage thing. And we just happened to be walking past a gravity take-up roller on a conveyor belt. And the gravity take-up roller, the bottom roller on it was at around about waist height. And of course, the conveyor was carrying a lot of particulate material. So a lot of dust was gathering at the base of the gravity take-up roller. And there was a shovel there. And it doesn't take much to think, well, if there's a shovel there, clearly this dust that's piling up underneath the gravity take-up roller needs to be removed. And what are you going to do to stop the person who's removing it from inevitably at some point in time, because it's possible it will happen, slipping into and getting taken up by the gravity take-up roller? It's a design. And similarly, you could go all through it. The whole thing smacks of design problems, even equipment, even process design problems, Mike, when you think about it. Getting rid of the people from the damaging areas, damaging energy areas, etc. It just screams design problems or design opportunities, I should say, to me.
Derek and Mike, when I look at this and I think about the principles we work with human-centered design, I would think this provides a really structural way to introduce a way of working and test it and design it through the human-centered design process. And so we then get that human factors approach and then combine the science and the human factors together. Does that make any sense, Mike, as a way of positioning this?
Yeah, I think so, Kelvin. I really like this presentation, and it gets me thinking about design and how we can better think about energy earlier.
Yeah,
I think it's very useful. I think also, it was really interesting to me, Derek. I really liked your comparison of the normative and the physical sciences. I thought that was a great comparison, something that safety professionals really need to think about. And I really liked what you said. You talked a little bit about the fads that we go through, and that's very frustrating. I know Kelvin and I talk about that quite a bit, and I'm sure folks on the call also feel the same way, perhaps. But you said energy is not a fad; it's a physical necessity for damage, and I thought that was really that's something that'll stick with me.
So I really appreciate everyone joining this webinar. We are going to do some more because there's some, obviously the application of this, there's some deeper material. We will do some webinars in that space. We will share some output. So we'll definitely share our summary of this with you all, and encourage you to get into the discussion about the energy damage model and how that we can get it more widely recognised as a tool in our safety toolbox. So thank you, everyone. Really appreciate you coming to join us at the Art of Work Academy, and look forward to having some future sessions around this space.